Hi guys, and welcome to yet another Codeforces Div3 round number 787. As you can see, the contest is still running, but I already solved all problems by getting a +1 in the process. But anyway, I think this contest is actually more educational than the previous one, so let's go over the problems. Problem A, food for animals. We had A packs of dog food, B packs of cat food, and C packs of universal food, and we had to feed X dogs and Y cats. Obviously, one dog or cat consumes one pack of food. So, what we do in this problem? There are certain conditions that are necessary. For example, the number of packs overall should be at least number of cats and dogs combined. The number of packs that are possible to feed cats with should be at least the number of cats, and same goes for dogs. And it turns out that these conditions are enough, so not only necessary but also sufficient. How to prove it? Well, first you give however many, like all possible packs of dog and cat only food, you give to them, and then you will see that C packs of universal food remains, and obviously like number of cats and dogs combined should not exceed C. So actually a better solution to this would be decrement x and y by C, and then just say that C is x plus y is at least C. But whatever. This is the way I solved it. In problem B, make it increasing, we had an array, we wanted to make it increasing. For that, we were allowed to divide any element by 2. We wanted to minimize number of operations. So in this problem, I noticed that it never makes sense to decrease the last element, because you want to be it greater than the previous one. So why, like the only constraint you have on the last element is that it has to be big. So why even decrease it? So since then we can notice that obvious greedy in reverse works. So if we encounter a new element going from right to left and we see that it's at least as big as the next one, we need to decrease this element. So we decrease. The only tricky situation is like if our number ever hits 0, then no matter how many times you divide by 2, you cannot become less than 0. So in this case, we just say that it's impossible. So yeah. In the next problem C, we had a painting. We put it into the gallery or like a room. And people visited the gallery, and one of them stole the painting. We had to find the number of possible thieves. Now, each person, after this entire situation happened, it told us if there was a painting or no painting when they entered the room. However, they sometimes cannot remember, which they encode as question mark. Also, like all good people who did not steal the painting, they tell the truth, but the thief can tell anything. So in this problem, I noticed that if any person says that they have seen a painting, then it's actually true. Like if the liar, if the thief says that he saw the painting when he entered the room, and it's true. So in particular, all people before the last one, they have seen the painting, and all people strictly before the last one, they cannot be thieves, because there was one person after them that testified that they are good. Similar argument in reverse applies with first 0. All people after first 0, they cannot be thieves, because this first 0 testified that when they came around, the painting was not here. Even if they are a thief and they are lying about not seeing the picture when they came in, it still means that for the next person, it will be already no painting. So actually all the following people are correctly saying that they have not seen the painting. And then all the people in between, they are undecided. We cannot determine which one of them stole the painting. So that's it. It actually took me a while to figure out the correct starting conditions, but eventually it worked. In the problem D, vertical path, we had a tree and we needed to partition it into minimal number of paths that go vertically. So like from parent to son, from parent to son. And we need to minimize the number of paths. So obvious lower bound on the number of passes is the number of leaves, because clearly any two different leaves, they belong to different passes. So then we just need to construct the actual passes itself. For that matter, we construct a graph and we run a DFS. DFS works as follows. As long as we are going down, we greedily construct passes. You can see that it always results in the optimal number of passes. As long as we are going down, we just add the vertex to the current path. However, once we step up, we cannot longer maintain the current path, we need to create a new one. With certain sanity conditions, like if the current path was empty, we don't need to insert a new path. And also the last path can become empty, so in that case we just discard it. But that is like details. The main idea is that the obvious lower bound that we show is achievable, as is often the case in competitive programming problems. Like if you have some mathematical lower bound on the answer, then maybe it is actually achievable. And greedy construction works for this problem. So I think it's actually a good problem, like explaining to people how things work in life. In problem E, we had a string of lowercase Latin letters. We were allowed to replace all occurrence of given character with the previous character, and we want to find the lexicographically minimal string that we can obtain. And we were also given the limit on the number of operations. So what I noticed is I said, let's maintain the mapping. What character gets changed to what? Initially, the mapping is identity. Every time we encounter a new character, we obviously want to minimize the first character that we see. So first we try applying all previous operations that were already made. Also apply to this character, because all operations apply to all characters of given kind, not in the same letter. So for these operations, we already paid in terms of operations. Now, as long as we can make more operations and the current character is not minimized, we make an operation, decrease this character, and we again can apply operations that we already paid for by reshuffling. Like let's say we perform operations from the back to the front. So first replace all occurrences of, if we ever replace letter Z with letter Y, then it can be the first operation that we make. If we ever replace Y with X, then it can be the second operation that we ever make. This way, operations will chain together and we pay minimum for replacing Z to X. If we have both Z and Y that we want to replace with X, then it's clearly optimal to first replace Z and then replace Y. So yeah, all operations that we make, they can be applied in correct order from last to first. So this is a valid condition. We already paid for these operations. After performing this operation, we can update our mapping. And it may sound like a lot of work, but it's actually clear that both of these iterations, they take at most alphabet size time, which is 26, so n times 26 is fast enough even with map constant. I don't know why I have map, probably because I didn't want to subtract a every time I want to access a character. So yeah, but that was fast enough, clearly. In the next problem, I somehow managed to get TLE. I, to this point, do not know why, but anyway, in this problem we have a tree-like city, and we want to start at vertex X, visit given set of vertices, and go to Y. So in this problem there are several observations that can be made. First of all, you clearly need to visit a convex hull of X, Y, and all AIs. And convex hull on a tree can be defined in terms of distances. Like if you have or shortest path. For example, if you want to visit vertices X and Y, then entire path between them has to be visited. Same with entire path between X and A1. So how to compute this thing? Well, first we need to construct the graph, also record for each vertex whether we want to visit or not, which is true for all AIs and also for X and Y. By the way, you may not have known, but you can create for loops like that in C++ 17, I believe, and forwards. So how to compute this convex hull on a tree? Well, for each, once we know which vertices we want to know, we can run DFS, and for each vertex count how many vertices in each subtree we want to visit. If there is at least one, then we should visit this vertex as well. And this, by the way, works because we rooted our tree. At X, so one of the vertices that we want to visit. So clearly the entire path also needs to be visited. So all vertices in which subtree we want to visit at least one vertex, and subtree includes the vertex itself. Then this vertex also has to be visited. So clearly we need to visit all these non-zero vertices. Now this is a subtree, but not like it is a subgraph that is also a tree, let's say it this way. So it has an Euler Tor that this Euler Tor, it's like a way to visit all vertices. No, a way to go over all edges exactly once in one order, in one direction, in other direction. This Euler Tor is that long. And like it's sort of well known that the distance you need to travel if you have a fixed starting point, fixed ending point, and to visit all vertices, it's like Euler tree except for the reverse path from Y to X. So there is a path that starts at X, goes, visits all the vertices, visits Y, and then gets back to X. Obviously, we do not need to get back to X, so we subtract this distance. And distance we also computed in DFS. For some mysterious reason, my first submission TL'd. The only differences is that I used set here and also had like 3 arrays instead of 2, and then another loop to count non-zero elements. I do not understand what is the difference between these submissions in terms of dramatically changing running time. But apparently there is some difference. I will need to look back into this later. In problem G, sorting pancakes, we had m pancakes and n dishes, and we wanted to sort them in non-increasing order. So like each next dish has less than or equal number of pancakes. And for this we were allowed to move one pancake to an adjacent dish in 1 unit of time. So what I did dynamic programming, but instead of like finding ways to satisfy to sort prefix of dishes, I was basically trying to find a way to sort prefix of pancakes, not increasing. So I have dynamic programming that for a given number of dishes and number of pancakes determines the fastest way to sort these pancakes into these dishes in such a way that last dish gets that many pancakes. So how to do this? Very easy in O of n to the fourth time. I'm kidding. It's actually much faster than n to the fourth because let's say n is equal to m. Just imagine. Then last dish cannot have more than one pancake. So like if there are 100 plates, 100 pancakes, because the pancakes are not increasing, if last dish has 2 pancakes, then all dishes have 2 pancakes, and that's already 200 pancakes in total. That's too much. So my reasoning here is that values in this keys in this map, and therefore the size of the map, will be increasingly small as we continue to increase the number of plates. So yeah. And now how to compute such a dynamic programming? Well, we loop over how many plates we already used, how many pancakes we already used. We can clearly see that it's optimal to use pancakes in order, like take some prefix of pancakes, put it into the first dish, take next segment, put it into the second dish, etc. Then we can loop over last value, and last value is important for ensuring non-increasing condition. And also, so this is like however many pancakes were in the ice dish, and what was the number of operations required to achieve such a situation. When we sorted j first pancakes into I first plates, such that last plate contains k, v is the cheapest way to do it. Then we loop over how many pancakes will go into the next dish. Obviously, it cannot be greater than k, but also like number of pancakes should be. There should be that many pancakes. Then we just create like it's because we are going to take minimum, we need some to initialize with infinitely large values. So now the only question that we have is to have to find transition cost. Well, transition cost means that we're putting pancakes between j's and j plus l's into the ice dish. Well, we can pre-compute it. To answer this cost question in O of 1 time, judging by my running time, it could have been done in a slower way, but whatever. So maybe even having a naive loop here works, but obviously you can use prefix sums to tell you what will be the cost. So cost is eventually prefix sums of absolute difference between position of j's pancake and ice plate. This value is how far we need to move j's pancakes for it to end up in the ice position. And by computing prefix sums of this cost for a fixed position, we can quickly tell how many operations it will take us to move some subsegment of pancakes into some position with this kind of expression. And then just check what is the cheapest way to no matter what is the number of pancakes in the last plate, because if m is significantly bigger than n, let's say we only have 10 dishes and 200 pancakes, then last plate can contain up to 20 pancakes. But still, you can already see that 20 is much less than m. So this loop, at least for large I, will be much faster than O of m. And this loop is obviously also fast for large for small k or large j. So yeah, this is the contest for you. I got a terrible penalty because I was also recording a screencast and because I got wrong submission here, but we are still like doing pretty well, I think. We can go into common standings on the third page. Like high international master performance, this is roughly what I am, so it makes sense to have such a performance. So yeah, thanks everyone for watching, and I will see you, I want to say tomorrow, with a Codeforces Division 2 round. So tomorrow will be Friday. So yeah, thanks everyone for watching, bye bye guys, see you next time.